Your Bitcoin wallet has an expiration date. Not from regulation, not from a hack, but from a math problem that a new kind of computer might eventually solve. When that day comes, anyone with the right machine could forge your signature and spend your coins. Roughly 4 to 6 million Bitcoin are already sitting in addresses that would be immediately vulnerable. And the biggest stash of all, 1.1 million coins worth over $100 billion, belongs to someone who hasn't been seen in 17 years. Stick around, because the clock is ticking and almost nobody in crypto is ready. Here's how your crypto actually works, in plain English. When you send someone Bitcoin, you're not handing them a coin. You're broadcasting a message to the network. I, the owner of this address, authorize moving half a Bitcoin to that address. You prove you own it by attaching a digital signature, a number generated from your private key, a secret only you have. The network checks that signature against your public key, a number everyone can see. If it matches, the transaction goes through. The scheme Bitcoin uses is called ECDSA, short for elliptic curve digital signature algorithm. It works because multiplying a point on an elliptic curve is easy, but reversing that math to figure out someone's private key is, as far as anyone knows, computationally impossible. That impossibility is the entire ballgame. Take it away, and anyone can forge your signature. Anyone can spend your coins. This isn't a Bitcoin-specific problem. Ethereum uses the same curve. Solana, Cardano, Polkadot, almost every chain uses elliptic curve signatures or related public key cryptography. The whole industry, roughly $2 trillion in market value as of mid-2026, sits on the same mathematical assumption. In 1994, a mathematician at Bell Labs named Peter Shor published an algorithm that solves that exact math problem on a quantum computer. Polynomial time, which roughly means fast enough to be practical. A sufficiently large quantum computer could take your public key, run Shor's algorithm, and produce your private key. Your signature becomes forgeable. Your coins become spendable by whoever has the machine. As of 2026, no such machine exists. The best quantum processors, IBM's Heron line, have 156 programmable qubits. Breaking a single Bitcoin key would require somewhere between 1.5 million and 20 million physical qubits, depending on assumptions about error correction. The gap is 4 orders of magnitude, but the direction of travel is clear, and the cryptography community has been preparing for this transition for over a decade. The codes have been broken before. The last time it happened, the breakers stayed quiet for years. In the 1930s, the German military adopted a machine called Enigma. It scrambled messages through rotating wheels with billions of possible settings. They used it for practically every military communication: army orders, navy positions, logistics, weather reports. They assumed the number of configurations made it unbreakable. They were wrong. In 1932, a Polish mathematician named Marian Rejewski cracked it using group theory and a replica machine they called the bomb. When Germany invaded Poland in 1939, the Polish team passed their work to the British in French. At Bletchley Park in England, a team led by Alan Turing turned the break into an industrial-scale decryption operation. The Allies were reading German Enigma traffic for most of the war. The Germans never knew. The lesson the cryptography world took from Enigma: security through perceived complexity is not security. The Germans believed the machine was too complex to break because they couldn't imagine how to break it. The breakers had a decisive advantage for years and kept quiet the whole time. That parallel matters for what's coming. Jump to the 1970s. The US needed a standard encryption algorithm. In 1977, NIST adopted the Data Encryption Standard, or DES, with a 56-bit key. That meant roughly 72 quadrillion possible keys. At the time, that seemed like a lot. 2 Stanford cryptographers, Whitfield Diffie and Martin Hellman, said a dedicated machine could brute force it. The NSA, which had pushed for the shorter key, disagreed. Diffie and Hellman were right. The Electronic Frontier Foundation built a machine for about $250,000 that found a DES key by brute force in 56 hours. The next year, a distributed effort broke a key in 22 hours and 15 minutes. The standard that protected banking, government data, and corporate secrets was broken by a machine that cost less than a house. NIST ran a public competition to find a replacement. 15 algorithms were submitted from around the world. After years of public analysis, NIST selected Ryan, designed by two Belgian cryptographers, as the Advanced Encryption Standard, or AES. The DES to AES migration took roughly 25 years from adoption to effective retirement. Even public breaks take decades to fix. The quantum transition will be harder, because the thing being upgraded is not a government standard. It's a decentralized network with no central authority and $1 trillion of value held by people who may not agree on the solution. If you're finding this useful, hit subscribe. We don't do hype here. We do the math behind your money, and there's a lot more math coming. Now, which parts of crypto actually break, and which ones survive? Cryptocurrency uses 3 cryptographic tools. First, hash functions. Bitcoin uses SHA-256 to link blocks together and power mining. Second, symmetric encryption, which wallet software uses to protect your private key file. Third, public key signatures, which authorize transactions. Only the third one breaks. Shor's algorithm cracks public key cryptography. For hashes and symmetric encryption, the relevant quantum algorithm is Grover's, published in 1996, which only gives a square root speedup. That effectively halves the key length. SHA-256 under Grover's attack still has about 128 bits of security. That's still considered safe. So the quantum threat is specific. It doesn't break mining. It doesn't break the blockchain's integrity. It doesn't break the hash linking that makes blocks tamper-proof. What it breaks is the signature scheme that says you own your coins. A quantum computer running Shor's algorithm against Bitcoin's curve could take a public key and compute the private key. Once it has the private key, it can sign transactions on your behalf and move your coins to its own address. The attack targets the signature layer, nothing else. The rest of the internet is already moving. In August 2024, NIST published the first post-quantum cryptography standards. ML-Chem for key exchange, ML-DSA for signatures, and SLH-DSA as a backup. Cloudflare, which handles about 20% of all web traffic, has been testing post-quantum connections since 2022. Apple added post-quantum encryption to iMessage. Signal implemented it too. The web is being rebuilt piece by piece. Now look at cryptocurrency. Bitcoin has no formal post-quantum plan. No adopted proposal for quantum-resistant signatures. The topic comes up periodically and then recedes. Ethereum has had more discussion, but nothing deployed. A few smaller projects moved faster. QRL was built from the ground up with hash-based signatures. Algorand uses a lattice-based scheme, but these are niche. The reason the major chains haven't moved isn't ignorance. The developers know. The reason is governance. Deploying a new signature scheme requires every node, every miner, every exchange, and every wallet to upgrade at the same time. If they don't, the chain splits. And there's a practical problem. Post-quantum signatures are much larger. A Bitcoin signature today is about 72 bytes. A dilithium signature is about 2,700 bytes, roughly 38 times larger. That means bigger transactions and higher fees. So how far away is the threat? Breaking a 256-bit Bitcoin key with Shor's algorithm needs roughly 2,300 logical qubits. But logical qubits don't exist in isolation. Each one is built from many physical qubits because quantum computers are noisy and need error correction. With current error rates around 0.1%, you need about 1,000 physical qubits per logical one. Multiply it out. Roughly 2.3 million physical qubits. Other estimates range from 1.5 million to 20 million, depending on assumptions. The best machine today, IBM's Heron, has 156 programmable qubits. The gap is 4 orders of magnitude. Qubit counts have roughly doubled every 2 to 3 years. At that pace, you reach the millions in the 2050s. IBM's roadmap targets a large-scale fault-tolerant machine by 2029. That doesn't mean breaking Bitcoin in 2029. It means demonstrating the prerequisite. The earliest plausible break is the mid-2030s. There's a framework called Mosca's theorem that puts it simply. If the time you need to keep data secure plus the time to migrate is greater than the time until a quantum computer arrives, you have a problem. For crypto, the data is permanent. The blockchain is public. Every exposed key is already sitting there, waiting. Now count the coins at risk. Of roughly 19.8 million Bitcoin mined, about 4 to 6 million sit in addresses with exposed public keys. The largest single bucket belongs to Satoshi Nakamoto. The creator of Bitcoin mined roughly 1.1 million coins in 2009 in addresses where the public key is directly recorded on the blockchain. They've never moved. If a quantum computer can run Shor's algorithm, Satoshi's stash is the first thing that becomes forgeable. At $100,000 per coin, that's $110 billion. Whoever builds the first machine would have a strong incentive to attack those coins first. They're the largest concentration of exposed Bitcoin, and they're believed to be unmonitored. And if 1.1 million Bitcoin suddenly moved from addresses dormant for 17 years, every exchange and every holder would assume the worst. The price would crash before anyone could confirm whether it was a legitimate transfer or a quantum forgery. Beyond Satoshi's stash, millions more are exposed through address reuse. Some of those coins are lost forever, with nobody watching them. A quantum attacker could drain them, and nobody would notice until the transaction appeared on the blockchain. So what actually happens when the threat becomes real? 4 scenarios. 1. Orderly migration. The community agrees on a quantum-resistant scheme. Users move their coins over months or years. The network upgrades. This needs about a decade of lead time and near-universal cooperation from a community that spent years fighting about block size. 2. Panic fork. A quantum milestone spooks the market. Bitcoin drops 30% in a day. Developers rush a fork. The community fractures over which scheme to use. Some users lose coins in the confusion. The old chain keeps running with vulnerable addresses. It takes years to recover. 3. Silent attack. A nation-state builds the machine and says nothing. They drain wallets slowly, mixing coins through privacy services. The first sign is unexplained transactions from dormant addresses. Then someone notices Satoshi's coins moving. By then the damage is done. 4. Nothing happens for a very long time. Progress stalls. The threat recedes like Y2K. Possible, but you can't plan for maybe it never happens. And it's not just crypto. The same math protects every HTTPS connection, every banking login, every encrypted chat. A quantum computer that breaks Bitcoin signatures can also impersonate your bank's server. Intelligence agencies are believed to be collecting encrypted traffic now, storing it, planning to decrypt it later. For crypto, the harvest is already done. The blockchain is public. Every exposed key is sitting there, waiting. The most dangerous scenario isn't a public announcement. It's a silent capability, used selectively, discovered too late. So what should you actually do? The threat is real but not imminent. The gap between 156 qubits and millions is enormous. You don't need to sell tomorrow, but not all your crypto is equally at risk. If you use modern Bech32 addresses, the ones starting with BC1, and you never reuse them, your public key stays hidden until you spend. That's a harder attack. If you use old addresses starting with 1, or you've reused addresses, your public key is already visible. Move to a fresh Bech32 address and don't reuse it. And when Bitcoin eventually upgrades to quantum-resistant signatures, there will be a deadline. Coins left in old addresses after that deadline are permanently vulnerable. You'll need to move them yourself. Pay attention. Your crypto is protected by math. The math has an expiration date. Nobody knows the exact date, but the people who study this for a living believe it falls somewhere in the 2030s or 2040s. The fix exists. It hasn't been applied to the crypto you own. Team real threat or team overblown panic? Drop your answer in the comments and subscribe.